In this video, we'll introduce the idea of radicals and simple reactions that radical species undergo. A radical is a carbon, at least as far as this class is concerned. A radical is going to be a carbon that has a single unpaired electron. These are very reactive species because typically electrons like to be paired. In addition, notice that if we draw out a Lewis structure for this particular compound, that this carbon is only surrounded by 7 electrons, so it doesn't have a full octet. And so for both of those reasons, because it has an unpaired electron, because it doesn't have a full octet, radicals are extremely reactive species. I put this picture here of the hole in the ozone layer above Antarctica because radical reactions of these chlorofluorocarbons are responsible for the degradation of the ozone layer. So in order to understand those reactions, in order to understand the environmental consequence of radical species, we need to understand their structure and factors that lead to stability or instability of radicals, and then we'll introduce one reaction of radicals, which is the chlorination of methane, which is industrially useful. Okay. So as I just mentioned, radicals are, we're going to define radicals as carbons that possess an unpaired electron. So again, if we draw out the Lewis dot structure here, we have something that looks like this, right? What we're going to do is we're going to take this unpaired electron and we're going to place it in an unhybridized p orbital. So we're going to treat these radical species as sp2 hybridized with a single electron in this p orbital, which is perpendicular to the plane of the molecule. In some cases, the book mentions that you can have something resembling an sp3 hybridized structure. We're not really going to worry about that. So just assume that radicals are flat. So why would that be? Well, we can understand this structure if we recall the structure of similar compounds, essentially other reactive intermediates called carbocations that you might remember, or carbanions. So if you have 2 electrons, right, if you have a carbon that has a pair of electrons, it has a negative charge, so these 2 electrons will repel these other groups of electrons, push them down into an sp3 kind of configuration. Whereas if you have an empty p orbital, like in a carbocation, now those groups of electrons can spread out and you get a flat sp2 hybridization. I want everyone to think about the reactivity of radicals as being very similar to the reactivity of a carbocation, which makes sense, right? Because if we compare a carbocation to a radical structure, right, this lacks an electron. So this carbon is electron poor. It wants an additional electron to complete that octet. This carbon is also electron poor. So I think it's helpful when you're thinking about reactions of radicals to compare those reactions to those of carbocations. Okay, let's move on here. So now that we're thinking about carbocations, it might make sense that as we increase the substitution on our radical, the stability increases, just like in a carbocation, right? So this is going to be called a methyl radical. This is a primary radical. For example, CH3 CH2 dot. Ethyl radical would be primary. A secondary radical would be something like this. Now we have 2 carbons bonded to the carbon that has an unpaired electron. A tertiary radical would look something like this, right? So as substitution increases on our radical, the stability is going to increase. Tertiary will be the most stable, whereas methyl will be the least stable. You might remember why, but let's refresh our memories. So if we remember back to carbocations, and their stability, what we said is that hyperconjugation is responsible for that stability. So again, what we have, remember, what we have is an unpaired electron in a p orbital that's perpendicular to the plane of the molecule, right? So for every CH bond that's on one carbon away, that bond has 2 electrons, and those electrons can help to stabilize, can overlap slightly with that p orbital, funnel a little bit of electron density in there, and since that's an electron poor carbon, funneling that electron density into that orbital will be stabilizing, right? So the more carbons that you have bonded to the carbon that possesses a radical, the more stable it is. Notice for a primary radical, we have 1 hyperconjugative effect. With the isopropyl radical, we have 2, and with a tert-butyl radical, we have 3. So each one of these bonds that's overlapping with that p orbital creates something that resembles a pi bond that can stabilize that unpaired electron. Okay. So now that we know that, then can we rationalize something that we're going to be talking about a lot in terms of radical reactions, which is called the homolytic bond dissociation energy, sometimes abbreviated BDE. So what do we mean when we say homolytic? Well, lytic, it typically means to break. So this means that we're going to break a bond, and we're going to do it in a way that gives 1 electron to both atoms that are involved in the bond. This is different than what we've seen previously. Usually we see 2 electrons go to 1 atom and none go to the other atom. That's called heterolytic. Okay, so let's imagine what would happen if we broke this bond and we gave 1 electron to this hydrogen and we gave 1 electron to this carbon. Well, what we would get is a methyl radical and a hydrogen radical. So we would get these 2 species, right? If we broke this bond, if we broke this bond, now we would get a primary radical plus that same hydrogen radical. Here we would get a secondary radical. Here we would get a tertiary radical. So notice that the stability of the radical is increasing as we increase the substitution, right? So it makes sense, hopefully it makes sense, that this CH bond requires 439 kilojoules of energy to break. This one only requires 423. This one only requires 414. This only requires 406. So do you need to memorize those? Of course not. But what you do need to know is that as we increase the substitution on this carbon, this bond actually becomes weaker, which makes sense, right? Because if we break that bond, we're forming a more stable radical. So just to sort of summarize, right, if we're going to break this bond and form a more stable radical, so this is a more stable tertiary radical, then that's going to be a weaker bond. In order to break this bond, we have to make a less stable methyl radical, so that's going to be a stronger bond. So CH bonds that will lead to more stable radicals are going to be weaker. CH bonds that are going to lead to less stable radicals are going to be stronger. It's going to take more energy to break that bond because you're forming a higher energy species that's less stable. Okay. What about this scenario? So we just said that tertiary CH bonds, if we go back for a second, we just said tertiary bonds are the weakest. So if we generalize here, we can say tertiary CH bonds are the weakest, and methyl CH bonds are the strongest, right? So let's look at some other patterns and try to rationalize those, right? So we can get even weaker bonds, right? So here's the tertiary CH bond at 406. Now allylic CH bonds, even though this one isn't even tertiary, is actually weaker than the tertiary. Benzylic CH bonds are even weaker than that. Why would that be? Well, remember that any way that we can spread out electrons through resonance is going to be a stabilizing effect. So resonance stabilized radicals, are going to be the most stable, we'll say. And so you want to look for allylic CH bonds or benzylic CH bonds. Okay. So how do we use arrows to show one electron moving? What we're familiar with is, for example, both electrons from a bond go to this Y species. So we get a positively charged species and a negatively charged species with a lone pair of electrons. So each prong of the arrow sort of represents one electron. So this kind of an arrow represents two electrons moving. So how are we going to show one electron? Well, we're going to use a fishhook arrow that essentially only has one prong. So this arrow means one electron from the bond went to Y. This electron means one electron from the bond went to X. So now the resulting products, each species has a single unpaired electron. So we generated two radicals from homolytic bond cleavage. The bond broke, each atom got one electron, as opposed to heterolytic bond cleavage. Okay, so let's look at an example of how we can use these arrows to depict a radical mechanism. The most simple radical mechanism is the chlorination of methane. Methane, CH4, also known as natural gas, is readily abundant and available. We can chlorinate it using chlorine, and H nu is a fancy way of saying light. So if we shine light on this reaction, the result is we get methyl chloride and hydrochloric acid. The first thing I want you to think about when you're looking at radical reactions, like we talked about before, if you look at the homolytic bond cleavage energy for all the different kinds of bonds that are in your reactants, this is going to help you figure out what the first step is, right? So we have methane, which is just a bunch of CH bonds, and we have chlorine gas, which is a chlorine bond. So if we're putting energy into the system in the form of light, we want to decide which bond is the weakest, because that's the one that's going to break first if we put in energy, right? So we can go here to our bond dissociation energies, and what we see is that this chlorine-chlorine bond is really, really weak. Only 243 kilojoules per mole of energy is required to break that homolytically. So this is the bond that's going to break first and generate a radical. Okay? So let's draw out the whole mechanism here on the next slide. So the mechanism of the chlorination of methane is called a radical chain mechanism, and you'll understand why once we go through all the steps. The first step in any radical chain mechanism is going to be an initiation step, and we already said that the first step is that we homolytically break the weakest bond. In this case, it's breaking the chlorine-chlorine bond. So what are we going to get? We're going to get two chlorine radicals. So in order for a radical mechanism to take place, we have to form radicals. So the initiation step forms those radicals, typically through a homolytic bond cleavage event. Okay, so now let's think about the net reaction. Remember, what we had was methane plus chlorine goes to chloromethane plus HCl. So what do we mix together? Well, we've mixed together chlorine and methane, and we shine light on it. So when we generate this chlorine radical, it has a choice. The only things that are in the reaction right now are methane or more chlorine. If the chlorine radical reacts with more chlorine, then we just get the same things that we started with, right? But if the chlorine radical reacts with methane, then we start forming new species. And let's look at those species. So these are going to be called our propagation steps. So methane can bump in to a chlorine radical, And this chlorine radical is very hungry for electrons, right? It has an unpaired electron and wants to steal an electron away from any bond that it sees. So what it does is it takes an electron away from any one of these CH bonds to form a new HCl bond, and then this bond becomes an unpaired electron on carbon. So we get a methyl radical plus our first product, which is HCl. Now what does this methyl radical see? Well, it sees more methane and more chlorine, right? Chlorine has the weakest homolytic bond cleavage energy. So what's going to happen is that methyl radical will want to steal an electron away from chlorine. And when we do that, we form a carbon-chlorine bond, and we regenerate a chlorine radical, which is important. So now we've formed our two products here, and most importantly, we've generated a chlorine radical again. So this is called a radical chain mechanism, right? Because all we need, theoretically, all we need is one chlorine radical, because the chlorine radical will react with methane to generate a methyl radical. The methyl radical will react with chlorine to regenerate the chlorine radical, which can go back and consume another molecule of methane. And this can happen over and over and over again. So you want to think about this as a cycle, which can happen thousands of times until you've consumed all your reactants. So eventually you've consumed all your methane, you've consumed all your chlorine, and all you have left is these radical species that are floating around, these really high energy species. It's very unlikely, since these things are formed in such small quantities, that two radical species are going to find one another. So the only time that these termination steps are possible is once we've consumed all of our reactants. And so in the termination step, we can combine two chlorine radicals to give us Cl2. We can combine two methyl radicals to give us very small quantities of ethane, or we can combine a chlorine radical and a methyl radical to give us one more molecule of chloromethane. So to summarize, an initiation step, usually there's only going to be one initiation step, and that's where radicals are formed. You want to break the weakest bond. The propagation step, you start with radicals and you end with radicals. So radicals are in the reactants and the products, and these propagation steps together can happen over and over and over again. That's why it's called a radical chain mechanism. Once we've consumed all our starting material, these radicals can react with one another. So we have radicals in the reactants but none in the products. Those are called termination steps. Okay, so the net, really all you want to do is focus on your propagation steps, because the net result of your propagation step is the net reaction of methane and chlorine are consumed to form chloromethane and hydrochloric acid. Okay, so to summarize, what I want you to know about radical reactions, what I want you to take away from this video, is that radicals occur by homolytic bond breaking. Each atom gets one electron, those are both radicals. We're going to depict that bond breaking event using fishhook arrows that show one electron moving. The radicals are extremely reactive because they don't obey the octet rule, they're electron poor. We can use radical stability to understand CH bond strengths. I want you to be able to identify trends in CH bond strengths, which ones are the most stable, which ones are the least stable. I want you to be able to understand stability of radicals, which ones are the most stable, which ones are the least stable, and I want you to be able to give initiation, propagation, and termination steps for straightforward radical halogenation reactions.